Marching on with Euclidean geometry. On today's show, an old favorite, but one we haven't been able to talk about yet because we've needed Euclidean geometry to do it, and we've needed similar triangles to do it. And so we are actually going to discuss Venema's proof of the Pythagorean theorem. There are zillions of proofs of the Pythagorean theorem. I recognize that zillions is not a number, but it's close enough to a number for our purposes. So here's what Venema does with the Pythagorean theorem. He says, take any right triangle A, B, C, right angle at C. If C isn't where the right angle is, change the letters on the vertices so that we get C is the right angle, A and B are the acute angles. The side opposite from angle A is traditionally given the length little a, and the side opposite angle B is traditionally called little b, and the side opposite angle C is traditionally called little c. Now do this weird thing. Drop the perpendicular from C to line AB and let that hit maybe, I don't know, call that F for foot of the perpendicular. And give these little lengths X and Y. If you will notice, there is one right triangle in the problem, well, in the diagram, but there are also two other right triangles in the diagram, and we will color code them for convenience. Those are three right triangles. Now, consider red and green. Red and green share angle B, and they are each right triangles. And so the red triangle is similar to the green one. Similarly, so the blue triangle and the green triangle share angle A, and they are each right triangles. And so the blue triangle is similar to the green triangle by angle-angle similarity. But if the red triangle is similar to the green triangle and the blue triangle is similar to the green triangle, then the red triangle is similar to the blue triangle. I have three right triangles that are similar each to the other two. And so I can say that corresponding sides of similar triangles are in proportion. I can say that X is to A as A is to C. I can say that the small leg is to the hypotenuse of the red triangle as the small leg is to the hypotenuse on the green triangle. And so I have that A squared is X times C. Likewise, I can say that Y over B is B over C, because the big leg to the hypotenuse on the blue triangle compares to the big leg and the hypotenuse on the green triangle. And so by algebra, I have B squared is Y times C. So I am going to combine those two pieces of information and say that A squared plus B squared is X plus Y times C. But wait a minute, X plus Y, that is C. Done. The Pythagorean theorem can be proven by similar triangles. The Pythagorean theorem can be proven by similar triangles. It's a nifty proof. It's not the only proof. If you were to Google proof of Pythagorean theorem, you would find scads of possible proofs of the Pythagorean theorem. This is not Euclid's proof of it. This is algebra, but it flows from similar triangles. And so that's sort of what I was hoping that we would play with a little bit. I will also play in this particular video cast with that height and how that height compares to some of the others, looking for some right triangle stuff. So let's copy all of this and paste it here. Great. Let's look at this height h. This is the altitude of the right triangle. It's the altitude to the hypotenuse. I argue that x is to h as h is to y. You should pause for a moment and think about why that is true. X is to h as h is to y. That's the small leg to the big leg on the red triangle, and the small leg to the big leg on the blue triangle. Now, curiously, algebraically speaking, this phenomenon, this idea where that h quantity is in both means, both mean position in the proportion, means that h is the geometric mean. Right, I can spell. I need my eraser tool. It's the geometric mean between x and y. If I want to know what h squared is, that's x times y. So that's an interesting thing to notice. It flows from similar triangles. Similarly, I notice that x is to a as a is to c. And you should pause for a moment to figure out why that is true. This is the small leg and the hypotenuse on the red triangle. This is the small leg and the hypotenuse on the green triangle. Again, we have this funny phenomenon taking place, which means that A is the geometric mean between X and C, which roughly translated into English means that each leg of the right triangle, each leg of the original right triangle, is the geometric mean between the whole hypotenuse and the projection of the leg onto the hypotenuse. So if I had a gorilla up here at infinity shining a flashlight down, this side would project its shadow on the hypotenuse. The leg is the geometric mean between its shadow and the whole hypotenuse. So you should get very familiar with this picture. You should love this picture. This is a nice picture to love. There's a lot of similar triangles going on here, a lot of things to be aware of, a lot of relationships to know, and that is our quick look at the Pythagorean theorem and some similarity in general. Okay.